Imagine a scenario for a second. Just picture this.
Okay.
An attacker is sitting, thousands of miles away,
Right.
and they have just found a tiny flaw in your application code.
A single vulnerability.
Exactly. And they use that tiny flaw to essentially trick your own server into asking for its own master administrative keys.
Which is usually game over.
In a normal data center or a poorly configured cloud environment. Absolutely game over. The attacker gets the keys, they take over your entire infrastructure, and you are having literally the worst day of your career.
They call your lawyers.
Yeah, exactly. But in modern AWS architecture, something frankly insane happens.
It really is wild.
The server actually generates the packet containing those stolen keys.
It does. It creates the payload.
But because of a hard-coded rule deep in the network protocol, that specific packet mathematically realizes it shouldn't exist in a routed state.
Yes.
And it violently destroys itself before it can ever leave the physical machine.
The attacker gets absolutely nothing.
Nothing at all.
It's one of the most elegant defense mechanisms in modern cloud security.
It's beautiful engineering.
It really is. It's taking a layer 7 application vulnerability, a human error in code, and neutralizing it with a pure layer 3 networking hack.
And that is exactly the kind of engineering we are looking at today. Welcome to this custom-tailored deep dive designed specifically for you into the systems engineering of Amazon EC2.
We're getting into the weeds today.
Oh, we are. We aren't just reading off a basic spec sheet here.
No.
Our mission today is to extract the really vital nuggets of knowledge from a massive stack of sources.
We're talking technical white papers, invent architecture presentations.
Deeply technical security blogs, the whole 9 yards. You are here to understand the why behind modern cloud computing.
How it physically actually works.
Right, because the cloud isn't just magic.
It is not. It's millions of interconnected physical components.
And if there is a recurring theme we're going to see across all these sources today, it is this concept of tearing down legacy anti-patterns.
Yes, that is the core of it all.
We are going to look repeatedly at how AWS had to completely rip out the old ways of doing things.
Because you can't scale the old ways.
Right. You have to rip them out to achieve the hyperscale and the mathematically proven security we see today.
It's a complete paradigm shift.
So on the docket, we're going to cover the AWS Nitro system, dive into the physics of the Graviton 5 custom silicon wall.
Which is mind-blowing.
It is. We'll untangle exactly how networking adapters like ENA and EFA function, weigh the architectural trade-offs of where your data actually lives.
And we'll look at that brilliant packet-destroying security layer you mentioned.
Yes, IMDS v2. I love this stuff.
Pure problem solving.
It's unadulterated problem solving. But to understand where we are now, we kind of have to understand the mess we left behind.
We do. We have to look under the hood at the foundational bedrock of the cloud, which is virtualization.
Right.
To really grasp the sheer power of a modern EC2 instance, you have to understand the architectural debt that the entire industry carried for over a decade.
It was a huge burden.
Massive. In the early days of cloud computing, everyone, relied on standard software hypervisors.
Right.
For AWS and many others, the standard was an open-source hypervisor called Xen.
Okay, let's establish a baseline here, just for anyone who might be, adjacent to infrastructure.
Sure.
Conceptually, a hypervisor is just the software that allows one physical computer to pretend to be multiple different independent computers, right?
Oh, exactly. It's the management layer. It's the illusionist.
The illusionist, I like that.
But in a traditional Xen architecture, that management was handled by a massive monolithic software domain.
Usually called what, DOM0?
Yes, DOM0, domain 0.
Right.
This DOM0 software ran directly on the main physical CPU of the server.
Right alongside the customer.
Right alongside all the customer virtual machines. And it was responsible for doing, well, literally everything.
Okay, define everything in this context, because the server is doing a lot of different jobs at any given microsecond.
Everything means it allocated the physical CPU cycles. It managed the physical memory space.
Okay.
It handled every single storage input and output operation.
So every read and write?
Every single one. If a virtual machine needed to write a file to a virtual hard drive, DOM0 had to intercept that request.
Oh, wow.
And then it had to translate it to the physical storage. If a packet came in from the internet, DOM Zero had to route it through a software switch.
Before it even got to the VM.
Yes, and deliver it to the correct virtual machine. Plus, it handled all the management APIs, the security group firewalls, the monitoring metrics, all of it.
Okay, I can immediately see the bottleneck here.
It's glaring.
If you have one giant piece of software intercepting every single read, write, and network packet for, say, 50 different virtual machines on a server,
Yeah.
that software is going to consume a massive amount of the server's actual computing power.
It's the ultimate legacy anti-pattern.
Yep.
We call it the virtualization tax.
The virtualization tax.
From an engineering perspective, every CPU cycle that DOM spends routing a network packet is a CPU cycle that the customer is not getting to use for their actual application.
Right. You're paying for compute you can't use.
Exactly.
Yeah.
You end up with these massive physical servers where 20, maybe 30, sometimes even 40% of the processing power is just eaten up by management overhead.
That is terribly inefficient.
And it creates that classic nightmare scenario,
The noisy neighbor.
the noisy neighbor.
Oh man, I remember this. I was running a database on a shared host back in roughly like 2013.
Oh, the dark ages.
Truly. And randomly at 2 a.m. on a Tuesday, my database would just grind to an absolute halt.
Just zero throughput.
Zero. It took me weeks to figure out what was happening.
What was it?
Another customer on the exact same physical server rack had spun up a script to mine early Bitcoin.
Oh, of course. Always crypto.
Always. And their virtual machine was maxing out the CPU and the network queues.
Yep.
And DOM Zero was working so hard to accommodate their massive traffic that it essentially starved my virtual machine of resources.
Yep.
My application crashed because of someone else's traffic.
That is the textbook noisy neighbor problem.
It was infuriating.
Because DOM Zero is a shared software bottleneck, your performance is directly at the mercy of whoever happens to be sharing the physical silicon with you.
Right.
But beyond performance, think about the security implications.
Oh, right.
You have millions of lines of complex code handling every single hardware interaction in one centralized place.
It's an incredibly attractive target.
Exactly. If an attacker finds a single vulnerability in DOM Zero, they theoretically have the keys to the entire physical server.
And every customer machine running on it.
Every single one. So AWS realized this monolithic software approach was a fundamental dead end.
You just can't scale that.
You simply cannot reach hyperscale while paying a 30% performance tax on every server you buy.
That realization birthed what they call the AWS Nitro system, right?
Yes. The Nitro system completely shifted the paradigm when it fully rolled out with the C5 instances back in roughly 2017.
Okay, so what did they actually do?
They decided to stop doing virtualization in software and start doing it in hardware.
So they broke DOM Zero apart.
Completely dismantled it.
The sources describe Nitro as a microservices hardware architecture.
Yes.
What does that actually look like inside the server rack?
It's built on 3 distinct pillars. Let's break down the first one.
Okay,
The Nitro cards.
right.
AWS took all those heavy I/O functions that DOM Zero used to do, the network routing, the storage encryption, the metric.
And they ripped them out of the main CPU entirely.
Exactly. Instead, they built dedicated proprietary hardware components that plug directly into the PCIe bus of the server.
Okay, let's unpack this for a second. It's like moving from a legacy company where the CEO is doing all the accounting, marketing, and janitorial work. Right. To a modern corporation where the CEO only makes high-level decisions and dedicated department heads handle the rest.
That's a great analogy. The Nitro cards are the department heads.
But wait, back up a second. The sources throw around acronyms like ASICs and FPGAs when talking about these Nitro cards.
Right.
What is the physical engineering difference here, and why does it actually matter?
It's a crucial distinction. Let's start with FPGA. It stands for Field Programmable Gate Array.
Okay.
It is essentially a blank slate of silicon.
A blank slate.
You can write hardware-level code and flash it onto the FPGA, and the silicon physically configures its logic gates to perform that specific task.
So it physically changes its wiring?
Effectively, yes.
Yeah.
It's incredibly fast, but crucially, it is reprogrammable.
Oh, okay.
If AWS invents a better routing algorithm, they can just update the FPGA over the network.
So it's hardware that can learn new tricks.
Exactly. Now, what about an ASIC?
Right.
ASIC stands for Application-Specific Integrated Circuit.
Okay.
This is when you are so confident in your design that you permanently etch the logic into the silicon. You cannot reprogram an ASIC.
It's baked in.
It does exactly one job, but it does it faster and more efficiently than any other piece of hardware on the planet.
Okay, so AWS uses a mix of both.
Yes. depending on the specific instance generation.
So instead of a software program running on the main CPU trying to juggle network traffic,
Yes.
there is literally a dedicated physical silicon card plugged into the motherboard whose only existence is to route network packets.
That's all it does.
And another physical card whose only job is to manage the encrypted storage drives.
Exactly. And they communicate directly over the PCI bus, which is that massive high-speed data highway on the motherboard.
So because these massive operations are offloaded to dedicated silicon, the main CPU is almost entirely freed up.
The customer's guest virtual machine gets to use practically 100% of the physical server's resources.
The virtualization tax is gone.
Completely. And the noisy neighbor problem is virtually eliminated because there is no shared software bottleneck managing the I/O.
Wow. Which brings us to the security aspect.
Right.
If the network and storage are handled by these peripheral cards, who is watching the actual motherboard?
That leads us to the second pillar of the Nitro system.
Okay. What is it?
The Nitro security chip.
Okay.
This isn't a peripheral card you plug in. It is a custom piece of silicon integrated directly into the physical motherboard of the server itself.
Oh, it's soldered on.
Yes. And it acts as the hardware root of trust.
Now, what does root of trust actually mean in a physical engineering sense?
It means it is the ultimate, unquestionable authority on the state of that hardware.
Okay.
When a server boots up, before the main CPU even starts processing instructions, the Nitro security chip wakes up.
It's the first thing alive.
Exactly. Its job is to continuously monitor, protect, and cryptographically verify the system firmware.
So it's measuring things.
It measures the exact state of the motherboard. If it detects that any unauthorized modifications have been made to the hardware,
Like what?
say a malicious actor tried to flash a compromised BIOS onto the server, the security chip will simply refuse to let the system boot, or it will instantly isolate it from the AWS network.
It just cuts it off.
Completely.
Because that security is handled at a physical hardware level, independent of the main processor, the sources highlight that this is what actually enables AWS to offer bare metal instances.
Yes.
I always wondered how they did that safely.
Right. A customer can rent an entire massive physical server.
They don't even get a virtual machine.
No, they get direct access to the raw silicon.
But AWS can do that safely because the Nitro security chip and the Nitro cards are still operating in the background.
Exactly. Entirely isolated from the main CPU, managing the infrastructure, and enforcing network boundaries without the customer ever being able to touch them.
Okay, so we have the Nitro cards handling I/O.
Right.
And the security chip locking down the motherboard.
Right.
That leaves the third pillar, which manages the actual virtualization if you aren't running bare metal.
Exactly, the Nitro hypervisor. Because all the heavy lifting has been offloaded to the cards, the hypervisor software doesn't have much left to do.
It's just a shell of its former self.
It is. AWS built a custom, heavily stripped-down version of KVM.
Which stands for kernel-based virtual machine.
Right. And we are talking about a minimalist system of roughly 50,000 lines of code.
Compared to the millions of lines in the old as in DOM.
It's a fraction of the size. Its only job is acting as a very simple traffic cop.
So what does it actually do?
It just allocates physical memory spaces and physical CPU cores to the guest virtual machines. That's literally it.
I want to look at the philosophy behind this because it's fascinating.
It's separation of concerns.
Strict separation,
Right.
and the sources make a point that I think is really easily missed here.
What's that?
The communication design between the AWS control plane and the actual server is strictly passive. Can you break that down?
Oh, this is critical for security. In a legacy system, the server's main CPU had to run management agents that actively talked back to the cloud provider's central network.
It was constantly phoning home.
Right. In the Nitro architecture, the Nitro controller card is the only component that talks to the AWS management network.
Okay.
The main board of the server, where your virtual machine actually lives, does not have a management network connection.
Wait, so even an AWS engineer with the highest level of clearance physically cannot SSH into the main board of the server hosting my virtual machine?
They cannot. The architecture physically prevents it.
That is wild.
The Nitro controller only accepts tightly defined API calls like spin up a new VM or attach a new hard drive.
It is a passive restricted gateway.
There is no mechanism for human access to the host.
It's a brilliant way to eliminate human error or insider threat.
Absolutely.
So we've moved the storage, the networking, and the security to separate physical components.
Right.
But the fundamental reality of a public cloud is still multi-tenancy.
Always.
My virtual machine might be processing, sensitive financial data.
Yeah.
And it is sitting in the exact same physical RAM sticks and using the exact same physical CPU caches as a virtual machine owned by a complete stranger.
Or a malicious actor.
Exactly. So how do we guarantee the isolation on the motherboard itself?
That is the million-dollar question in cloud computing.
Right.
And it brings us to the cutting edge of what the industry calls confidential computing.
Okay.
Specifically, we need to look at the new 6th-generation Nitro system, which introduced something truly groundbreaking.
The Nitro Isolation Engine, or NIE.
Yes.
Up until this point, even with Nitro, public cloud multi-tenancy relied on what the sources call soft isolation.
Right. The hypervisor software enforced the boundaries.
Between virtual machines, and while heavily locked down, any software, no matter how good, can theoretically have a zero-day bug.
Right. If there is a bug in how the hypervisor manages memory pointers,
Yeah.
one virtual machine might accidentally or maliciously read the memory space of another virtual machine.
Right.
AWS wanted to completely eliminate the word theoretically from that sentence.
They wanted hard isolation.
Hard, irrefutable isolation.
So they built the Nitro Isolation Engine. It's described as a new ultra-minimal separation kernel specifically designed to handle hardware-level memory boundaries and CPU register states.
Right.
And they wrote it entirely in Rust, which is a programming language famous for being memory safe.
Eliminates a whole class of memory errors.
But the real mind-bending part of the NIE isn't the language.
No, it's how they validate it.
Right. They don't just run software tests.
They use a process called formal verification.
Yes.
This is a massive paradigm shift in how we think about software security.
I want to spend some time here, because when I first read the term formal verification, honestly, my eyes glazed over a bit.
It sounds like academic jargon.
It does. I assumed it just meant really, really rigorous software testing.
It's so much more than that.
I mean, software testing today is incredibly advanced. We have automated fuzzers throwing millions of random inputs at code every second to see if it breaks.
Yeah.
How is formal verification actually different from just rigorous testing?
The distinction is absolute.
Wow.
And it fundamentally changes the definition of security.
Okay, lay it on me.
Think of it this way. Empirical testing, no matter how rigorous, no matter how many millions of inputs you fuzz, is ultimately just checking a massive list of known scenarios.
You're throwing stuff at the wall to see what sticks.
Exactly. You are looking for bugs.
Right.
But testing can only prove the presence of a bug if you happen to find one.
Right.
It can never, ever prove the absence of bugs.
Oh, because you can't test everything.
There is always the possibility of a zero-day exploit, some bizarre edge case combination of inputs that you simply didn't think to write a test for.
Because a modern processor has an essentially infinite state space.
Exactly.
You can't test every single combination of ones and zeros passing through a CPU.
It would take longer than the lifespan of the universe.
Right.
So let's use an analogy to make this concrete.
I love analogies. Go for it.
Imagine you have built a massive, complex labyrinth. A maze.
Okay, a big maze.
Testing the security of that maze is like dropping a million robotic mice into it.
Okay.
The mice run around randomly for a month. If none of the mice find the exit, you say, okay, empirical testing suggests there is no exit.
Right.
But you don't actually know. Maybe there is a hidden door that requires a very specific sequence of turns that no mouse happened to make.
Right, you just know that your specific test mice didn't find the exit.
Formal verification abandons the mice entirely.
No more mice.
Instead, formal verification takes the architectural blueprint of the maze.
Okay.
And it uses pure mathematical logic and algebraic equations to analyze the geometry of the walls.
Wow.
It mathematically calculates the contiguous boundaries and proves that the outer perimeter is solid.
It proves it.
It doesn't test scenarios. It dictates that an exit physically, mathematically, cannot exist.
That is wild.
It's powerful.
And the scale of this inside the Nitro Isolation Engine is staggering. The sources detail that AWS used a highly specialized proof-assistant software called Isabelle Hachol. They had to write a mathematically proven model of how virtual machine memory isolation should work.
And that mathematical proof comprises over 330,000 lines of machine-checked mathematics.
330,000 lines of math.
It is one of the largest continuous proofs of software correctness ever deployed in a commercial environment.
So how does it actually function in real time?
The main Nitro hypervisor we talked about earlier.
The 50,000 line one.
Right. It is actually deprivileged now.
Wait, really?
Yes, it does not have the authority to touch the memory state of a guest virtual machine.
So who does?
If the hypervisor needs to create a new VM or pause a VM, it has to ask the Nitro isolation engine to do it.
Ah.
The NIE then takes that request, checks it against its 330,000 lines of mathematical proofs.
Real time.
Yes. And only executes the command if it mathematically verifies that doing so will not violate the isolation boundaries of any other tenant.
It's not we didn't find any ways in. It's the laws of mathematics dictate there is no way in. It makes these instances the first in a major public cloud to carry formally verified hypervisor isolation in production.
It is a remarkable engineering achievement.
But let's push the envelope even further.
Let's do it.
What if you are dealing with data so incredibly sensitive, say, massive databases of unencrypted personally identifiable information, or the master cryptographic keys for a global banking network?
The crown jewels.
Right. What if it's so sensitive that you don't even trust the operating system running on your own virtual machine?
Right. Even if Nitro mathematically protects me from other customers, what if my own Linux server gets hacked because my team left a port open?
Exactly. For that absolute highest tier of paranoia, AWS built Nitro Enclaves.
Nitro Enclave.
A Nitro Enclave allows a customer to carve out a highly isolated compute environment directly from their existing EC2 instance.
Let's look at the mechanics of this because it's clever.
You literally allocate a specific number of CPU cores, right?
And a dedicated chunk of RAM.
And you tell the Nitro system, cut this away from my main virtual machine and put a vault door on it.
And the constraints on that vault are extreme.
How extreme.
It is designed to have the absolute smallest attack surface technically possible. First, a Nitro Enclave has absolutely no persistent storage. None. You cannot attach a hard drive to it.
Wow.
Second, it has zero interactive access.
Meaning I can't SSH into it?
Even if you are the root administrator of the parent EC2 instance, you cannot log into the enclave you just created.
So I can't even see what it's doing?
No. And third, it has absolutely no external networking.
No internet.
It does not have an IP address. It cannot route to the internet. It cannot talk to your local network. It is completely dark.
So if it has no storage, no network, and no login access, how on earth do you actually use it?
The isolation is absolute by design. The only way data gets in or out of that enclave is through a secure local virtual socket.
Called a VSOC.
Yes, a VSOC. This is the dedicated communication channel that connects the enclave solely to its parent EC2 instance.
Okay, so the workflow looks like this. Tell me if I'm getting this right.
Go for it.
I have a web application running on my main EC2 instance.
Right.
A user submits highly sensitive, encrypted credit card data.
Okay.
My main instance takes that encrypted data, passes it through the VSOC into the dark Nitro Enclave.
Yep.
The application running inside the enclave decrypts it, processes the payment, encrypts the confirmation, and sends it back out the VSOC to the parent instance.
Exactly.
And the parent instance and anyone who might have hacked the parent instance never sees the unencrypted credit card number.
That is the exact use case. But you just highlighted a massive engineering puzzle.
Oh, what's that?
If the enclave is completely cut off from the network, how did the application inside the enclave get the cryptographic keys it needs to decrypt the credit card data in the first place?
Oh.
Because it can't reach out to the internet to talk to the AWS Key Management Service, or KMS.
Wait, yeah, how does it... Because if you just pass the keys through the parent instance, a hacker on the parent instance could just steal the keys in transit.
Precisely.
So how does it work?
This is where cryptographic attestation comes in.
Okay.
And it is a beautiful piece of engineering trust.
Lay it out.
When you first initialize the Nitro Enclave, the underlying Nitro hypervisor, which sits below everything and sees the raw hardware,
Right.
it takes a very specific cryptographic measurement.
Measurement of what?
It calculates a unique mathematical hash of the enclave's base operating image, the exact application code running inside it, and the IAM security role of the parent instance.
It's basically taking a fingerprint of the software before it even boots up?
Yes. The hypervisor bundles all of these measurements into what is called an attestation document,
Okay.
and it digitally signs that document using the hardware root of trust.
The security chip we talked about earlier?
Exactly. It is essentially a highly secure, unforgeable ID card that proves exactly what code is running inside that dark vault.
Okay, so the Enclave has an ID card. How does it get the keys?
The Enclave hands this ID card to the parent instance through the VSOC.
Okay.
The parent instance takes the ID card and makes a standard API call out to the AWS Key Management Service saying, hey, I have an enclave here that needs decryption keys. Here is its ID.
And KMS doesn't just blindly hand over the keys.
No, KMS verifies the digital signature of the hypervisor.
Okay.
Then it looks at the fingerprint of the code inside the enclave. The customer will have pre-configured a rule in KMS that says only release the decryption keys if the enclave's code fingerprint exactly matches this known safe value.
Meaning, if a malicious actor somehow managed to inject even one single line of rogue code into the enclave application before it booted,
The entire mathematical hash would change completely.
the attestation would fail.
KMS would see that the fingerprint doesn't match the approved policy, and it would flat out refuse to release the decryption keys.
The data remains locked.
It's an incredible chain of trust.
The sources mention this enables things like multi-party computation.
Oh, that's a huge use case.
You could have two competing pharmaceutical companies, right? Put their proprietary, highly secret clinical trial data into a single Nitro enclave to run a joint machine learning analysis.
Yes. Neither company can see the other's data.
AWS cannot see the data,
Right.
but they both get the computed results securely. It solves the human trust problem by replacing it with hardware and math.
If we pull back and look at the bigger picture here, we now have a hardware foundation that is mathematically proven to be isolated, stripped of legacy overhead, with the ability to spin up cryptographic dark vaults on demand.
That is the chassis.
That's the chassis. But a secure chassis doesn't do any work on its own.
It needs an engine.
It needs an engine.
Which brings us to the raw compute power. Let's look at the engine roaring inside this chassis.
Let's do it.
And here's where AWS did something that shifted the entire industry. They didn't just buy off-the-shelf engines from Intel or AMD.
No, they didn't.
They started designing their own silicon. Let's talk about the Graviton 5 custom processor.
The custom silicon journey at AWS is a fascinating study in vertical integration.
Truly.
Years ago, AWS realized that to truly optimize the cloud environment, they couldn't just optimize the hypervisor or the network cards.
Right.
They needed to control the hardware stack all the way down to the processor instruction set.
To the atoms, basically.
They need to build CPUs specifically designed for cloud multi-tenancy from the ground up.
And they built this on the ARM architecture, right? Rather than the traditional x86 architecture used by Intel.
Yes.
Fast forward to today, and Graviton is an absolute juggernaut.
It is huge.
The sources note it has crossed a $20 billion annual run rate business for AWS.
$20 billion.
It accounts for more than half of all new CPU capacity they have added over the past 3 years.
And the newest iteration, which just hit general availability in mid-2026 inside the new M9G instance family, is Graviton 5.
From an engineering standpoint, the physical specifications on this chip are staggering.
They are. We are talking about a processor built on a 3-nanometer TSMC process.
Let's pause on that.
Okay.
3 nanometer. People hear these numbers and they just sound like marketing jargon.
It's hard to visualize.
Why does the physical size of the transistor on the silicon matter so much to a cloud provider?
It is the fundamental physics of computing.
Okay, teach me physics.
A transistor is essentially a microscopic switch that turns electricity on or off.
Representing a 1 or a 0.
Exactly. The smaller you can make that switch, the closer you can pack them together.
Okay.
3 nanometer is incomprehensibly small.
Yeah.
We are talking about structures that are only a few dozen atoms wide.
The width of a human hair is roughly 80,000 to 100,000 nanometers, just for context.
Right. So when transistors are that small and that close together, the electrons don't have to travel as far to move from one switch to the next.
Because the distance is shorter.
Exactly. Shorter travel distance means two massive benefits.
Which are?
Speed and efficiency. The chip can perform calculations much faster, and critically, it requires significantly less voltage to push the electrons across the gap.
Less power.
Less voltage means less heat generated.
Ah, and heat is the ultimate enemy of the data center.
Heat density is the absolute limiting factor for how much compute you can put in a server rack.
Right.
Because of the efficiency of the 3-nanometer process, AWS was able to pack a massive amount of performance into a single chip without melting the motherboard.
That makes sense.
Graviton 5 is divided across 4 chiplets, which is a manufacturing technique that increases yields and puts the memory controllers physically closer to the compute cores.
And the core count is massive.
Oh, yeah.
Graviton 5 boasts 192 physical cores. That is double the 96 cores found in the previous Graviton 4.
Double.
It is the first CPU in the entire AWS fleet to support PCIe Gen 6.
Which doubles the bandwidth to those Nitro cards we discussed earlier.
Right, and it supports ultra-high-speed DDR5 8800 memory.
Yep.
Plus, it features a massive L3 cache, topping out 192 megabytes, which is 5 times larger than the previous generation.
But here is where we circle back to that central theme of the day.
Tearing down legacy anti-patterns.
Yes, exactly. AWS made a very deliberate architectural choice with the entire Graviton line to completely abandon a technology called simultaneous multithreading, or SMT.
Now, in the Intel world, they famously call it hyperthreading.
Right.
Why is abandoning it a big deal?
Historically, SMT was a clever workaround. Traditional x86 processors from Intel and AMD have very large, complex, beefy execution cores.
Okay.
Often, a single thread of execution, a single task, doesn't need all the resources of that massive core at the same time.
Like it's overkill.
Kinda. For example, if a task needs to fetch data from the main memory, the core might stall for a few nanoseconds waiting for the data to arrive.
And in CPU time, a few nanoseconds is an eternity of wasted potential.
Exactly. So SMT was designed to squeeze more efficiency out of the silicon.
How?
It takes one physical core and presents it to the operating system as two virtual CPUs, or vCPUs.
Okay.
It allows two separate threads to share the underlying physical resources of that single core. While thread A is stalled waiting for memory, thread B can use the core's execution units to do some math.
That sounds great in theory. So why is it a legacy anti-pattern in the cloud?
Because sharing resources always creates contention.
Always.
What happens if thread A and thread B both suddenly need to do heavy math at the exact same microsecond?
They clash.
They clash. They have to wait in line. SMT essentially creates a micro-level noisy neighbor problem right there on the silicon die itself.
Oh, wow.
You have two threads fighting over the same L1 and L2 caches and the same execution pipelines.
So even if Nitro perfectly isolates my virtual machine from other customers, if my own application has two threads sharing a hyper-threaded core, they are slowing each other down.
Exactly. With Graviton 5, AWS said, we aren't doing that anymore.
Clean break.
Every single vCPU that a customer provisions maps directly, one-to-one, to an independent, dedicated physical execution core.
There is no sharing of pipelines, so it's like office space.
Okay, let's hear the analogy.
SMT, or hyperthreading, is like sharing a single, very large executive desk with a coworker. You both have your own laptops, you might get more work done overall for the company, but you are constantly bumping elbows.
You are.
You are fighting for the stapler. If they are on a loud phone call, you can't focus.
Right.
Graviton 5 doesn't give you a shared desk. It gives every single thread its own private executive office with a closed door. You get a real core per vCPU.
And that architectural purity means performance is incredibly consistent and predictable.
No fighting for the stapler.
You never have to worry that another thread is hogging the cache. And the performance metrics reflect that dedicated architecture.
AWS claims up to 25% better raw compute performance over Graviton 4.
Yes. But real-world, complex workloads see even bigger gains because of the lack of core contention.
Like what?
Web applications are running up to 35% faster.
Wow.
Relational databases see up to 30% faster operations.
But I'm going to push back here.
Okay, push back.
If Graviton is so much faster and cheaper, why doesn't every single customer just click the drop-down menu in the console and switch their fleet to Graviton 5 today? Is there a catch?
There's a transition cost.
Okay, what is it?
Graviton is built on the ARM instruction set architecture, much like the processor in your smartphone or modern Apple laptops.
Right.
The vast majority of legacy enterprise software was compiled for the x86 instruction set used by Intel and AMD.
So they don't speak the same language.
Exactly. You cannot simply copy an x86 application onto a Graviton server. It will not run. The processor literally speaks a different language.
So you have to recompile your software.
Yes. For modern applications written in interpreted languages like Python, Java, or Node.js, the switch is usually trivial.
You just pull a different version.
You just update your deployment script to pull the ARM version of the runtime, and it works flawlessly.
Okay, that's easy.
But if you have decades-old proprietary C++ code where the original developers have long since retired,
oh boy,
recompiling for ARM can be a significant engineering effort.
I can imagine. But for those who can make the leap, the target workload that AWS built Graviton 5 for is fascinating.
It is.
The sources highlight that Meta is deploying tens of millions of these Graviton 5 cores, specifically for something called agentic AI.
Agentic AI.
We need to define this because the general public hears AI, and they just think of a chatbot answering a question.
Right. Agentic AI is a completely different workload profile than a simple large language model chatbot.
How so?
Agentic AI refers to autonomous software agents that perform complex, multi-step task orchestration to achieve a high-level goal.
So instead of prompting, write me a Python script to scrape a website,
You prompt the agent, analyze my competitor's pricing strategy.
that's a big difference.
Huge. To do that, the agent has to break the problem down.
It has to think.
It decides to write a scraping script.
Yeah.
It executes that script. It reads the raw HTML data.
Right.
It writes another script to parse the HTML into a database. It analyzes the data, realizes it made an error, rewrites the script, and iterates until the goal is met.
Okay, but why does that demand such immense CPU power?
Wow.
The entire narrative in the tech industry right now is that AI requires massive arrays of GPUs from companies like NVIDIA. Why is Meta using Graviton 5 CPUs for this?
It is a crucial distinction in the math.
No.
GPU's graphics processing units are fantastic for one very specific thing: highly parallel matrix math.
Just crunching numbers.
That is the math required for training massive neural networks or generating a single massive response from a prompt. GPUs are like a factory with 10,000 workers who can each only do one very simple addition problem at a time.
But an agent isn't just doing matrix math, it is making logical decisions.
Precisely. Agents spend a vast majority of their time orchestrating.
They're managing.
They are evaluating complex logic trees, they're rapidly executing small Python scripts, they are making API calls to external software tools, and they are managing state across dozens of concurrent tasks.
So those operations are highly sequential and logic-heavy.
That is highly CPU-bound work.
You need a fast, smart manager, not 10,000 simple calculators.
Exactly. And because an agent might spawn hundreds of subtasks simultaneously, you need a massive concurrent environment with extremely fast context switching and extremely low latency between the cores.
And Graviton 5 gives you that.
Graviton 5, with its 192 independent physical cores, its massive 192 milligit L3 cache, and a new mesh architecture that reduces intercore latency by 33%, is tailor-made for that kind of orchestration at scale.
It keeps those agents thinking and acting without waiting around for CPU cycles.
Exactly.
Okay, so we have mathematically verified security, and we have 192 physical cores of raw, unshared, incredibly efficient power.
Right.
But here's the brutal reality of systems engineering. All of that compute power is completely, utterly useless if the data gets bottlenecked trying to enter or leave the chip.
Yep.
A processor core running at billions of cycles a second can't process data it doesn't have yet.
Data starvation is the silent killer of cloud performance.
Which brings us to the nervous system of the EC2 instance, the networking adapter.
A nervous system.
We need to untangle exactly how data gets from the internet to those 192 cores. The sources outline 3 distinct tiers of network interfaces: the ENI, the ENA, and the EFA.
Let's start with the baseline, the default adapter everyone gets. The ENI, or Elastic Network Interface.
This is your basic virtual network card.
Yes, but even the basic card has some impressive engineering behind it. ENIs utilize a technology called SRIOV,
which stands for Single Root I/O Virtualization. We promised to explain the acronym, so how does SRIOV physically work?
Imagine a massive high-speed physical network port on the back of the physical server.
Okay.
The hypervisor needs to share that single physical port among 50 different virtual machines.
Right.
In the old days, the DOM0 software would act as a virtual switch, intercepting every packet and routing it in software.
We already know that causes massive overhead.
SRIOV is a hardware standard that allows that single physical network interface to physically present itself as multiple, distinct virtual network devices right on the PCI bus.
It's a hardware-level illusion.
It is. The hardware literally splits itself into dozens of virtual functions. And each virtual machine gets its own dedicated virtual function that it interacts with, as if it were a physical network card.
It bypasses the software switch entirely.
Exactly. ENIs are solid, they support speeds up to 10 gigabits per second, and they're tied directly to a specific EC2 instance.
The sources note you might attach multiple ENIs to a single instance if you need to create a physically separate management network.
Or if you are running a virtual security appliance that needs to be dual-homed across 2 distinct subnets.
But 10 gigabits per second simply isn't enough bandwidth for modern, data-heavy applications.
Not anymore.
If you are serving high-definition video or streaming massive data sets, 10 GBPs will starve those 192 Graviton cores.
Which is why we step up to the next tier.
Yeah.
The ENA, the Elastic Network Adapter.
Okay.
This is the enhanced networking standard for modern instances. When you are running on a Nitro system, the ENA can push massive throughput, scaling up to 100 gigabits per second or even 200 GBPs on certain instance types.
That is massive.
It provides consistently lower latencies and can handle millions more packets per second.
And there is a fascinating new feature for ENA mentioned in the deep dive sources, released in mid-2025, called flexible ENA queue allocation.
Oh, yes.
This solves a really specific, highly technical engineering problem regarding how CPUs actually handle network traffic.
It does. To understand why this feature matters, you have to understand the mechanics of a CPU hardware interrupt.
Okay, break that down.
When a massive flood of network packets hits the ENA network card, the card doesn't just indiscriminately dump that data into the CPU's lap.
Right.
The card has to send an electrical signal, an interrupt, to tell the CPU, hey, stop what you are doing, I have data for you to process.
It's like knocking on the door.
Exactly. But if you have 192 cores, which core gets the interrupt?
Which door do you knock on?
Right. To manage this, the ENA uses hardware queues. It hashes the incoming packet data and assigns it to a specific queue. Each queue is essentially tied to a specific vCPU. This allows the network card to load balance the interrupt requests, so multiple vCPUs can process the incoming network traffic simultaneously in parallel.
That makes perfect sense. Keep all the cores busy.
But historically, the number of ENA queues assigned to an instance was statically allocated by AWS based on the instance size.
So it was fixed.
Let's say your instance was given 32 network queues. If you were running a hyper-intensive network application, say a custom packet inspection firewall,
Yeah.
you might completely max out the throughput capacity of those 32 queues. Your network interface becomes a bottleneck, dropping packets.
Even if the other 160 vCPUs on your Graviton 5 chip are sitting completely idle, twiddling their thumbs.
Exactly. The application is artificially constrained by the static queue allocation.
And flexible ENA queue allocation changes that.
Completely. It allows customers to dynamically allocate queues across their network interfaces from the instance's total available pool.
So if you have a network-heavy application, you can dynamically assign more queues to that specific ENA.
This distributes the packet processing interrupts across far more vCPUs, preventing any single core from becoming a choke point and unlocking the true throughput potential of the instance.
It is a brilliant lever for systems engineers to pull to keep data flowing smoothly.
It is.
But even ENA, with all its flexible queues and 100 GBPs bandwidth, has its limits when you start talking about the most extreme, specialized workloads on the planet.
The bleeding edge.
I'm talking about tightly coupled high-performance computing, like massive weather simulation models or distributed machine learning clusters, where thousands of GPUs across hundreds of servers act as a single brain.
For those workloads, standard networking simply isn't fast enough.
You need the EFA.
The elastic fabric adapter.
The EFA is a fundamentally different beast. Why isn't 100 GBP's ENA good enough for high-performance computing?
Because of the software overhead to Linux kernel.
The kernel itself is the bottleneck.
Yes. Tightly coupled HPC applications don't communicate using standard web traffic. They rely on something called MPI, the message passing interface.
Okay.
The nodes in the cluster need to exchange tiny fragments of data with each other with microsecond level latency.
Tiny but constant.
Exactly. If a packet has to go through the standard Linux networking stack, it has to be copied from the network card into kernel memory. The CPU has to process the IP headers, then process the TCP headers, handle congestion control, and finally copy the payload into the user space memory where the application lives.
It takes too long for the operating system to figure out where the packet goes.
Those microseconds of processing delay, multiplied across millions of messages a second, stall the entire computing cluster.
So the EFA introduces a revolutionary concept for cloud environments called OS bypass.
OS bypass.
Explain the mechanism of OS bypass.
It literally does exactly what it sounds like. It allows the MPI application running in user space to bypass the Linux kernel network stack entirely.
Just skips it.
The application uses a specialized memory-mapped I/O technique to communicate directly with a physical EFA hardware device sitting on the PCI bus.
The kernel is completely cut out of the data path.
Completely.
It is basically a direct fiber optic line between the application memory and the physical network card. No kernel memory copies, no TCP/IP processing overhead. The latency drops to almost nothing.
And the throughput becomes incredibly consistent, which is vital for synchronization across thousands of GPUs.
Now hang on, I have a pushback question here.
Say it on me.
If bypassing the OS with EFA makes everything so much faster, with drastically lower latency and higher throughput, why don't we just use EFA for every single EC2 instance?
That's a fair question.
Why do ENI and ENA even exist if OS bypass is objectively faster?
That is the core engineering trade-off of the network stack. OS bypass is a specialized surgical tool for a very specific job. When you bypass the Linux kernel, you are bypassing all the vital standard network processing that the kernel provides for normal operations.
Meaning I lose the internet, basically.
You lose standard TCP/IP routing.
Yeah.
You cannot route an OS bypass packet across the public internet. You lose the ability to apply standard security group rules at the OS firewall level because the kernel never sees the packet to inspect it.
Right. The firewall is blind to it.
OS bypass relies on a custom proprietary protocol designed specifically and exclusively for highly controlled node-to-node cluster communication within a single, tightly grouped network fabric.
So if I am running a general-purpose web server that needs to accept HTTP requests from random clients on the public internet, I need the Linux TCP/IP stack.
You absolutely do.
I need the routing tables, I need the congestion control, and I need the security layers.
Exactly. You cannot bypass the OS if the OS is doing work you actually depend on.
That makes perfect sense.
So for 99% of workloads, the ENA is the powerhouse you want. EFA is reserved strictly for those massive scientific and AI clusters where the cluster itself is acting as a single giant computer.
Different tools for fundamentally different data flows.
Precisely.
And speaking of data flows, once all that data is flying across the network at 100 GBPs and being processed by 192 cores, it eventually needs a place to park. It needs to rest.
Data persistence.
Exactly. This brings us to the storage trade-offs within EC2. Because storage in a cloud environment isn't just plugging a hard drive into a motherboard. It is an intricate set of engineering trade-offs between physical latency, data persistence, and concurrent sharing capabilities.
And this is exactly where a lot of cloud users get tripped up.
They do.
They look at a list of AWS storage services, EBS, EFS, Instance Store, and they don't know where to start.
It's alphabet soup.
It is.
Right.
The key is to completely ignore the service names at first. You have to start by analyzing your application's fundamental data access patterns.
Okay.
Is the data structured as raw blocks, hierarchical files, or API-driven objects? Do you need to share it simultaneously across multiple machines? Does the data need to survive if the server loses power?
Let's break down the big three mentioned in our sources. Let's start with the absolute fastest but most volatile option, the EC2 Instance Store.
Right. Instance Store provides raw, block-level storage. But unlike other cloud storage, it is physically directly attached to the host server running your EC2 instance.
So this isn't data traveling over a network cable.
No. These are physical NVMe solid-state drives plugged directly into the PCIe bus of the exact same motherboard that your virtual machine is running on.
Because it's a direct physical connection, utilizing the NVMe protocol, which bypasses older SATA bottlenecks, the latency is in the extreme sub-millisecond range.
It can deliver millions of IOPS input-output operations per second. The sources note it can be up to 10x faster than network-attached storage in specific heavy-read scenarios.
It is the equivalent of having a high-end SSD plugged directly into your personal laptop. But there is a massive critical catch to using it.
The catch is that Instance Store is entirely ephemeral.
Ephemeral.
The data on those physical drives only persists during the active lifecycle of that specific EC2 instance. If you stop the instance via the console, if you terminate it, or if the underlying physical hardware of the server suffers a failure, the data on the Instance Store is wiped clean and is gone forever.
It mathematically cannot be recovered.
Cannot.
So to be clear, you would never, ever put your primary authoritative customer database on an Instance Store volume.
Never. If the server reboots, your business loses its data.
What do you use it for then?
Instance Store is designed purely for the temporary storage of information that changes frequently and can be easily recreated.
Okay.
We're talking about fast-moving buffers, high-performance caches, scratch data, or temporary spooling directories.
Got it.
It is also excellent for large-scale distributed workloads like Hadoop MapReduce, where the data is replicated across dozens of nodes. So if one node fails and loses its ephemeral data, the cluster just pulls it from another node.
Okay, so if we need the data to survive a reboot, we need persistence. We need data that outlives the server. That brings us to EBS, the Elastic Block Store.
EBS is the absolute workhorse of EC2 storage. It provides persistent, highly durable block storage volumes.
Think of an EBS volume as a virtual hard drive that exists entirely separate from the compute hardware.
Yes. It is attached to your EC2 instance over a dedicated back-end AWS storage network.
The beauty of EBS is its independence. Because it lives on the network, you can shut down your EC2 instance, and the EBS volume retains its data safely.
Exactly. You can even detach the EBS volume from one server and attach it to a completely different server in seconds.
And it is incredibly reliable by design. The sources highlight that while an EBS volume is created within a single availability zone, which is essentially a physical data center behind the scenes, AWS automatically replicates your data across multiple redundant physical storage servers within that zone.
This architecture provides 99.99% availability and up to 99.999% data durability.
It's highly configurable, too. You can provision a volume anywhere from 1 gigabyte up to 16 terabytes.
And you can choose different underlying performance profiles based on your specific application needs.
Give me an example.
For a standard web server, you might use GP3, which is a general-purpose SSD offering a great balance of price and performance.
Sure.
But if you are running a massive legacy Oracle database that requires absolute guaranteed low-latency IOPS, you can provision an IO2 volume, which uses specialized hardware to guarantee that performance.
So EBS is essentially your personal, highly reliable, network-attached hard drive, but it has a limitation.
It does.
Generally speaking, an EBS volume is designed to be attached to exactly one EC2 instance at a time.
Right. It provides raw blocks of data, and the operating system of that single instance is responsible for formatting those blocks with a file system like ext4 and TFS and managing the file locking.
So what if my architecture isn't just one server? What if I have a massive auto-scaling cluster of 50 web servers, and they all need to read and write to the exact same shared directory of user-uploaded images at the exact same time?
EBS generally can't do that safely.
Yeah.
Because 50 different operating systems trying to manage the same raw blocks of data would corrupt the file system instantly.
Okay, so for that scenario, we must pivot from block storage to file storage. That brings us to EFS, the Elastic File System.
EFS shifts the paradigm. It is a fully managed serverless network file system utilizing the industry standard NFS version 4 protocol.
The defining superpower of EFS is concurrent shared access.
Yes, you can mount a single EFS file system onto thousands of Linux EC2 instances simultaneously.
Thousands.
And critically, those instances can span across multiple different availability zones.
It is a game changer for enterprise-wide file servers, massive content distribution networks, or big data analytics clusters where every node needs access to the same data set.
And it is truly elastic. With EBS, you have to guess how much storage you need, say 500 gigabytes, and pay for it up front.
Right.
With EFS, the storage size is practically unlimited, scaling into the petabytes, and you don't pre-provision anything.
The file system just grows and shrinks automatically as you add or delete individual files, and you only pay for the exact gigabytes you use.
However, there is an ironclad law of physics and networking here. Concurrency and distributed access require a trade-off in performance.
Break that down. Why is EFS slower than EBS?
Because EFS is a heavily distributed file system accessed over a network protocol by potentially thousands of concurrent clients, it has to manage incredibly complex distributed file locking mechanisms.
Why?
If server A and server B both try to write to the exact same file at the exact same millisecond, EFS has to arbitrate that conflict over the network to prevent corruption.
All of that coordination takes time.
Therefore, EFS simply cannot match the raw per-operation sub-millisecond disk latency of a dedicated single-tenant block device like EPS.
It just physically can't.
EFS provides excellent overall aggregate throughput for massive parallel jobs, but if your application requires the absolute lowest latency for millions of tiny sequential read and write operations like a highly transactional relational database, EFS is the wrong architectural choice.
To simplify the engineering trade-offs here, let's use an analogy.
Let's hear it.
Your instance store is like your brain's short-term working memory. It is incredibly fast, it's right there in your head, but when you go to sleep, or the instance stops, it's cleared out and forgotten.
Perfect.
EBS is like your personal laptop's hard drive. It is safe, it is persistent, it survives a reboot, but only you can use it.
Right.
EFS is like the company's shared Google Drive. Everyone in the enterprise can access it simultaneously, it scales forever, but it might take a fraction of a second longer to open a document because it's managing traffic from thousands of users over a network connection.
That perfectly encapsulates the access patterns. Match the pattern to the service.
Okay, we have covered a massive amount of architectural ground.
We really have.
We have secured the physical hardware by offloading I/O to the Nitro System ASICs and FPGAs. We have mathematically proven the memory boundaries with 330,000 lines of code in the isolation engine. We have maximized the compute efficiency by eliminating SMT and utilizing the 192 physical cores of Graviton 5. We've accelerated the network with dynamic ENA queues, and we've parked our data safely on persistent EBS volumes. From an infrastructure perspective, we have built an absolute impenetrable fortress.
We have. But here is the terrifying reality for infrastructure engineers. All of that world-class security focuses entirely on the layers below the customer's operating system.
Right. Which brings us back to the scenario we opened the show with.
The attacker in the darkroom.
What happens if the application running on top of all this mathematically secure infrastructure is fundamentally flawed? What if the customer's developer wrote sloppy code?
That is the nightmare scenario. You can have a titanium vault, but if the person inside the vault happily passes the combination lock out the window to a stranger, the vault is useless.
So true.
To understand how AWS mitigates application layer human error, we need to dive deep into the EC2 Instance Metadata Service, or IMDS, and the brilliant defense in depth of IMDS v2.
The IMDS is famous in cloud engineering circles. It resides at a very specific magic IP address, 169.254.169.254.
It is what's known as a link local address. By definition, within the networking protocol, a link local address cannot be routed over the public internet.
It stays inside.
It can only be accessed by software running directly, locally, on that specific physical network link, in this case, software running locally on the EC2 instance itself.
And the purpose of the IMDS is incredibly important. Over a decade ago, AWS created the service to solve a massive industry-wide security headache: hard-coded developer passwords.
In the old days, if an application needed to access an AWS database, developers would literally hard-code long-term AWS access keys, essentially a master username and password, directly into their application source code.
Which is terrible practice.
And inevitably, that source code would accidentally get uploaded to a public GitHub repository, and within seconds, automated bots would steal the keys and hijack the AWS account to mine cryptocurrency.
It was a disaster. So AWS said, stop hard-coding keys. Instead, assign an IAM security role to the EC2 instance itself.
Right.
Now, when the application boots up, instead of looking for a password in a file, it just sends an HTTP request to that magic local IP address, 169.254.169.254.
The IMDS receives the request, and it instantly generates and returns temporary, frequently rotating, short-lived IAM credentials.
The application uses those temporary keys for a few hours and then asks for new ones.
It is fantastic for security normally. The application just asks the local environment, who am I and what database permissions do I have? And it gets the keys it needs without any human managing a password file.
But as with all complex systems, solving one problem created a new vector for attack if the application itself has a vulnerability.
Specifically, it opened the door to a class of vulnerabilities known as server-side request forgery, or SSRF.
Let's explain the mechanics of SSRF quickly, because it is insidious. Normally, an attacker sitting on the internet cannot reach that 169.254 link local IP address. It's unrootable.
Correct.
But imagine your web application has a feature where a user can input a URL, say an image URL for their profile picture, and the server goes out and fetches that image.
If the developer didn't write strict validation code to check what URL the user typed in, that is an SSRF vulnerability.
Right. Because the attacker doesn't input an image URL. The attacker inputs the magic IMDS address, 169.254.169.254, latest metadata IAM security credentials.
Yes.
The attacker is essentially tricking your web application into making a web request on the attacker's behalf.
And because your web application is running locally on the EC2 instance, it has full, legitimate access to that link local IP.
So it asks for the keys.
The application queries the IMDS. The IMDS happily hands over the temporary IAM master credentials, and the vulnerable web application unknowingly takes those credentials and serves them right back out to the attacker's web browser.
Boom. The attacker just bypassed all your firewalls and now has the keys to your AWS kingdom, all because of a missing line of validation code in a profile picture upload feature.
And the sources point out it isn't just custom code SSRF. Misconfigured Open Web Application Firewalls, or WFs, and open reverse proxies can also be tricked into forwarding external traffic to the internal IMDS.
It became a massive industry problem. To combat this, AWS introduced IMDS version 2.
IMDS v2.
And the engineering behind IMDS v2 is brilliant because they didn't just patch a software bug, they engineered a belt and suspenders defense in-depth mechanism that relies on fundamental, lower-level networking rules to stop application layer attacks.
They assumed the code would be flawed and built physical safety nets. Let's break down the 3 distinct layers of defense in IMDS v2. Layer 1, the HTTP PUT request requirement.
Okay, what does that mean?
With IMDS v2, you cannot just fire a simple HTTP GET request to the metadata service anymore. A session must now be explicitly initiated by sending an HTTP PUT request to retrieve a secret session token.
Why does changing the HTTP method matter?
Because of how standard proxy software works. AWS analysis showed that the vast majority of misconfigured open WAFs and third-party reverse proxies are designed by default to blindly pass through standard GET and POST requests, because that's what normal web browsing uses.
Right, getting web pages and posting forms.
But they naturally block, drop, or require explicit configuration to pass through PUT requests, because PUT is an uncommon method that alters server state.
Oh. So if an attacker tries to use an open WAF to query the metadata, the attacker sends a PUT request, but the WAF itself drops the required PUT request at the edge.
The attack stops instantly without the IMDS ever seeing it. That is the belt. Now for the suspenders. Layer 2. The X-forwarded for header.
What's that?
When reverse proxies like Apache and Jinx or Squid forward a request on behalf of a client, they typically modify the HTTP headers. Specifically, they add a header called X-forwarded for to keep track of the original caller's IP address.
So the proxy is basically tagging the packet saying, hey, I'm delivering this for someone else.
Exactly. IMDS v2 is hard-coded to immediately inspect the headers of every incoming request. If it sees an X-forwarded for header, it instantly drops the connection.
Wow.
It is programmed to say, if this request came through a proxy, I am not talking to you. I only deal with direct local requests from the host OS. That shuts down the entire reverse proxy attack vector.
Which is incredibly smart. But here's where it gets really, really interesting. This is my favorite piece of engineering we are going to talk about today. Layer 3. The TTL equals one trick. This is the packet destroying mechanism I teased in the introduction.
The time to live hack. It is a stunningly elegant use of fundamental Internet Protocol architecture.
Let's dive deep into the mechanics of TTL. Every single IP packet sent across any network in the world has a specific metadata field in its header called time to live, or TTL.
It's essentially a counter.
When a computer generates a packet, it usually sets the TTL to a high number, like 64 or 128.
The purpose of TTL is to prevent network loops. Imagine a misconfigured router that accidentally sends a packet in a continuous circle forever. Eventually, thousands of these looping packets would clog the entire internet.
To prevent this, every single time a packet passes through a piece of Layer 3 network hardware, like a router, that device is mandated by the IP protocol to subtract 1 from the packet's TTL counter.
If the TTL counter ever hits exactly 0, the router realizes the packet has been traveling for too long, and it instantly drops and destroys the packet.
It's a self-destruct countdown timer based on physical network hops. So how does IMDS v2 weaponize this standard protocol?
When the IMDS v2 service responds to a valid PUT request, it has to send back that highly sensitive secret session token to the application. When it generates that return packet, it deliberately hard-codes the TTL field on that specific packet to exactly 1.
Meaning the packet containing the master keys has a lifespan of exactly 1 single network hop.
Precisely. If the software requesting the token is running legitimately, locally, on the EC2 instance itself, it receives the packet instantly via the local interface. The TTL is 1, no routing occurred, the packet arrives safely, and the application gets its keys.
But consider the complex attack scenario. What if the EC2 instance hasn't just suffered an SSRF vulnerability? What if the customer has severely misconfigured the EC2 instance to act as an open network router, a Layer 3 firewall, or a NAT gateway?
In that disastrous scenario, an external attacker might successfully route a request through the instance's routing table to reach the internal IMDS service.
And then what?
The IMDS receives the request, processes it, and generates the return packet containing the secret token, setting the TTL to 1.
The IMDS sends the packet back to the instance's network stack. But because the instance is acting as a router to forward the packet back outside to the attacker, it has to process the packet through its routing table.
And according to the fundamental laws of the Internet Protocol, when a router processes a packet to forward it to another interface, it must subtract 1 from the TTL.
The TTL of the secret token packet was 1. The router subtracts 1. 1 minus 1 is 0.
And the moment the TTL hits 0, the instance's own networking kernel destroys the packet. It vaporizes it.
The packet containing the stolen credentials is mathematically discarded by the server before it can ever reach the physical network card to leave the machine.
The attacker receives nothing. The stolen credentials literally cannot survive leaving the server. It is a brilliant Layer 3 networking physics hack designed to unilaterally stop a Layer 7 application vulnerability.
If we synthesize this, it is the ultimate masterclass example of defense in depth. AWS is assuming, as a foundational engineering principle, that the customer's application will eventually have flaws.
They assume a developer will introduce an SSRF vulnerability or misconfigure a routing table.
So they engineered physical and protocol level network rules, dropping PUTs, checking proxy headers, hard-coding TTL lifespans to physically contain the blast radius of human error. They are protecting the customer from themselves at the lowest possible layer of the stack.
It perfectly encapsulates the entire philosophy of the modern cloud. You don't rely on one layer of software to be perfect. You build a stack where the hardware, the math, and the protocols constantly cross-check and enforce boundaries.
We have covered an immense amount of complex engineering today. Let's briefly recap this journey. We started with the foundational bedrock of the AWS Nitro system, looking at how tearing down the massive monolithic DOM0 software hypervisor and offloading those I/O functions to dedicated custom-built physical PCIe, ASICs, and FPGAs eliminated the noisy neighbor problem and enabled true bare metal performance.
From there, we explored the absolute mathematical certainty of the Nitro isolation engine, relying on 330,000 lines of machine-checked algebraic proofs rather than empirical testing to guarantee memory boundaries. And we saw how Nitro enclaves use cryptographic attestation fingerprints to create impenetrable digital vaults.
We looked at the sheer unshared processing power of the 192 physical cores in the Graviton 5 custom silicon, exploring the physics of a 3-nanometer process and why eliminating hyperthreading makes it purpose-built to accelerate the CPU-bound sequential orchestration of agentic AI.
We untangled the nervous system, understanding how CPU interrupts work, why you use ENA with flexible queues for massive parallel web traffic, but switch to EFA and OS bypass to surgically remove the Linux kernel for tightly coupled HPC and machine learning clusters.
We weighed the stark trade-offs of where data lives, the ephemeral NVMe speed of instant store, the reliable replicated block persistence of EBS, and the massive concurrent shared scale of EFS. And finally, we looked at how IMDS v2 weaponizes clever Layer 3 networking tricks like TTL equals 1 to protect vulnerable applications from SSRF attacks.
It is a remarkable evolution from the murky shared environments of early cloud computing to a highly deterministic hardware-enforced architecture.
It really is. And looking at this massive stack of engineering, it leaves me with one final provocative thought for you to mull over. We've spent this entire deep dive looking at how cloud architecture has aggressively evolved. We are now living in an era where cloud multi-tenancy security isn't just enforced by good software policies. It is actively enforced by 330,000 lines of mathematically checked proofs and entirely custom physical silicon isolation.
A level of physical engineering and cryptographic research that quite literally costs tens of billions of dollars to develop and deploy.
Exactly. So the fundamental question we have to ask ourselves is, are we rapidly approaching a point, or have we already passed it, where the public cloud, this inherently shared multi-tenant environment, is actually significantly, demonstrably more secure than any private, air-gapped, on-premise data center a single enterprise company could ever afford to build for themselves? If the laws of mathematics can formally prove the public cloud is isolated, what does that mean for the future of on-premise infrastructure? Does a private actually mean secure anymore?
It is a question that challenges decades of traditional enterprise security thinking. The assumptions of the past no longer apply.
It challenges the very idea of what secure means in a physical sense. It turns out the muddy, shared waters of the public cloud have been relentlessly engineered into something far more solid and far more mathematically certain than the physical concrete of a traditional data center. Thank you so much for joining us on this deep dive. Keep questioning the architecture around you, keep looking under the hood, and keep exploring the why behind the technology you use every single day.